Ancient siege engines weighing tons and armies numbering in the thousands required logistical systems beyond simple supply lines. The Roman road network, constructed with standardized measurements, enabled rapid troop movement and resource distribution across vast territories. Material transport relied on a combination of maritime trade routes, overland roads, and a structured system of storage depots. This is Elias' Untold Vance. Invite you to analyze the hidden logistical mechanisms that sustained ancient warfare. This is Elias' Untold Vance. The logistical systems underpinning ancient military campaigns are rarely acknowledged beyond their immediate tactical applications. Yet, the Roman Empire's ability to project power across continents hinged on an infrastructure so meticulously engineered that it redefined mobility itself. Consider the Roman road network, a lattice of arteries stretching over 400,000 kilometers at its peak, with roads constructed using standardized dimensions, 8 feet wide for foot traffic and 30 feet high to accommodate wheeled transport. These specifications were not arbitrary, but derived from empirical calculations balancing durability, speed, and the mechanical limits of ancient vehicles. The roadbeds themselves were layered in a sequence of materials. Subsoil was compacted with wooden rammers, followed by a foundation of gravel for drainage, then sand to act as a binding medium. Finally, crushed stone or concrete formed the surface, creating a structure capable of withstanding heavy traffic and adverse weather. This stratification ensured that roads remained functional even after centuries of use, reducing maintenance costs and enabling consistent troop movement. The economic implications were profound. By standardizing road construction, the Romans minimized regional disparities in infrastructure quality, allowing for the efficient transport of goods between provinces. This system facilitated not only military supply chains but also the rapid deployment of legions to distant frontiers, a feat critical during campaigns such as those against the Parthians or Germanic tribes. The roads' alignment often followed natural topography to minimize earthworks, yet they also included aqueducts and milestones, engineering solutions that combined practicality with long-term planning. Such foresight ensured that resources like grain, timber, and weapons could be moved across vast distances without the logistical bottlenecks that plagued earlier civilizations. By embedding economic efficiency into their infrastructure, the Romans created a model of mobility that would influence transportation networks for millennia. This is not merely about roads. It is about the silent mechanisms that enabled an empire to sustain itself through sheer technological precision. The logistical frameworks underpinning ancient warfare were not confined to terrestrial networks alone. Maritime corridors functioned as arteries of sustenance and strategic mobility. In regions where overland transport was hindered by rugged terrain or hostile forces, coastal civilizations engineered vast maritime systems that rivaled their land-based counterparts in complexity. The Mediterranean Sea, for instance, became a conduit for the movement of grain from Egypt's Nile Valley to Roman military garrisons in North Africa and Italy. Phoenician merchants, leveraging their advanced shipbuilding techniques, double-hulled vessels reinforced with cedar planking, transited these routes with precision, carrying amphorae filled with olive oil, wine, and staple grains that sustained armies during prolonged campaigns. The economic interdependence of port cities such as Alexandria, Carthage, and Syracuse created a symbiotic relationship between commercial interests and military objectives, where the profitability of trade directly influenced the availability of resources for warfare. The Red Sea corridor further exemplifies this integration, with monsoon-driven currents enabling Indian Ocean merchants to transport incense, ivory, and iron tools to Arabian and African ports. These materials were not merely luxuries, but critical components in the production of weapons and fortifications. Roman engineers, recognizing the strategic value of maritime logistics, constructed lighthouse systems along key coastal points, such as the pharaohs of Alexandria, to guide vessels safely through treacherous waters. The economic impact of these networks was profound. Surplus grain from Egypt's fertile lands could be redirected to feed legions in Gaul or Britain, while timber harvested from the Black Sea region was transported via the Bosporus to fuel shipbuilding efforts in the Mediterranean. Sociologically, maritime logistics required coordinated labor systems that extended beyond sailors and merchants. Coastal communities developed specialized roles: dock workers, navigators, and shipwrights, who were often integrated into military hierarchies during times of conflict. In Carthage, for example, the state maintained a fleet of merchant vessels that could be rapidly repurposed as warships, blurring the lines between commerce and defense. The economic efficiency of these systems was further enhanced by standardized cargo containers, woven reed baskets, and wooden crates that minimized loss during transport. Taxation policies imposed on maritime trade also played a crucial role. Roman emperors levied tariffs on goods passing through their ports, generating revenue that funded the construction of roads, warehouses, and granaries, essential to sustaining military operations inland. The technological ingenuity of ancient mariners was equally pivotal. Greek triremes, with their three-tiered rowing banks and reinforced hulls, demonstrated an understanding of hydrodynamics that allowed them to outmaneuver larger vessels in naval battles. These ships were not only weapons of war, but also mobile depots capable of carrying provisions for extended campaigns. In the Indian Ocean, the use of lateen sails, triangular canvas rigging, enabled sailors to harness wind patterns more effectively than their Mediterranean counterparts, facilitating year-round trade between East Africa and Southeast Asia. The economic value of these innovations was immense. A single well-maintained fleet could ensure the uninterrupted flow of supplies to a front line, while its disruption could cripple an empire's ability to wage war. The sociological mechanisms underpinning these systems were equally intricate. In societies where maritime trade was central to survival, social classes often aligned with economic roles. Shipowners wielded political influence akin to landowning elites, while sailors formed guilds that negotiated labor terms and safety standards. These structures ensured the continuity of supply chains even during periods of conflict, as seen in the Han Dynasty's use of riverine networks along the Yangtze to transport iron ore from southern mines to northern fortifications. The economic interdependence between coastal regions and inland military hubs created a feedback loop. Armies relied on trade for sustenance, while merchants depended on military security to protect their investments. This dynamic was particularly evident in the Ptolemaic Kingdom, where Egyptian grain exports were safeguarded by Roman naval patrols, ensuring that both parties benefited from mutual stability. By the time of the late classical period, maritime logistics had evolved into a sophisticated science, with detailed records kept on cargo volumes, fuel consumption, and route efficiency. The Syracusan mathematician Archimedes, while best known for his work in physics, also contributed to naval engineering by designing screw propellers that improved ship maneuverability, a concept later adopted by Roman engineers. These advancements were not merely technical. They represented a cultural shift toward viewing logistics as a discipline requiring mathematical precision and strategic foresight. The economic impact of this shift was measured in the sheer scale of operations. During Julius Caesar's Gallic Wars, for example, over 100,000 tons of grain and timber were transported annually through Mediterranean ports to support Rome's campaigns in Gaul. In conclusion, the maritime logistics systems of antiquity were far more than passive channels for resource distribution. They were dynamic infrastructures that shaped the trajectories of empires. The technological innovations, ranging from ship design to navigational aids and economic frameworks, such as taxation and trade agreements, created a resilient network capable of sustaining large-scale warfare. These mechanisms did not merely enable conquests. They ensured the survival of civilizations by transforming oceans into highways of commerce and conflict, where every amphora of grain or roll of timber carried the weight of history's most enduring struggle. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. Storage depots formed the critical nexus where economic planning intersected with military necessity, creating a network that sustained prolonged campaigns across diverse terrains. These facilities were not merely passive repositories. They were engineered solutions to the logistical challenges of moving supplies over vast distances. In the Roman Empire, for example, viae militares, military roads, were constructed with precise gradients and drainage systems to facilitate the movement of wagons carrying grain, amphorae of olive oil, and timber for siege engines. Along these routes, depots were strategically placed at intervals determined by the maximum range of pack animals and the rate of resource consumption per soldier. A typical legionary camp required 15 kilograms of food per man daily, necessitating a constant flow of supplies from centralized storage points to frontline encampments. The materials stored in these depots reflected both immediate combat needs and long-term strategic goals. Foodstuffs were preserved through sun-drying, salting, or fermentation, techniques that extended shelf life by months. Weapons and armor were stored in dry, elevated locations to prevent corrosion, while siege equipment such as battering rams and ballistae required specialized shelters to protect them from the elements. In Mesopotamian campaigns, Sumerians utilized mud brick storage silos reinforced with bitumen to store surplus barley, a staple that could be ground into flour or brewed into beer for distribution among troops. These depots were often fortified with palisades and watchtowers, reflecting their dual role as supply hubs and defensive outposts. Economically, the establishment of such systems required meticulous resource allocation. The Roman nona militaris, a state-funded grain dole, was managed through a hierarchy of granaries, from provincial warehouses to local horia, ensuring that surplus harvests were redirected toward military use, rather than being lost to spoilage or alwish. Localized shortages. This system demanded an intricate understanding of agricultural cycles and transportation logistics. In the Qin dynasty, for instance, standardized weights and measures facilitated the rapid redistribution of stored resources across China's fragmented road networks, a practice that mirrored the Roman Malite system but adapted to East Asian topography. The labor required to maintain these depots was another economic factor. Skilled artisans were employed to construct and repair storage infrastructure, while large numbers of conscripted or enslaved workers managed inventory, transported goods, and secured facilities against raids. In Carthage, Phoenician merchants leveraged their maritime expertise to establish coastal depots that served as transshipment points for overland caravans, blending naval logistics with land-based supply chains. These systems required not only physical labor but also administrative oversight. Scribes recorded inventory levels using cuneiform tablets or wax seals, ensuring accountability in a world without modern accounting practices. Sociologically, storage depots acted as catalysts for the development of specialized roles within ancient societies. In regions where military campaigns were frequent, communities near depot locations often evolved into semi-permanent settlements, with populations dependent on the economic activity generated by military supply chains. This created a class of laborers and traders who became indispensable to the success of prolonged wars. Conversely, the concentration of resources in depot sometimes led to localized inflation or scarcity, as seen in the Han Dynasty's efforts to regulate grain prices near frontier garrisons. The technological innovation behind these systems was equally profound. In Greece, the use of wooden rollers and primitive pulleys allowed for the efficient movement of heavy loads into storage facilities, while the invention of the agorge, a system of military training, ensured that soldiers were adept at both combat and logistics tasks. The Persians, with their vast empire, developed an early form of supply chain management through a network of relay stations where horses and carts were exchanged to maintain speed across deserts and mountains. These techniques were not merely practical. They represented an early form of systems engineering applied to the scale of entire civilizations. The impact of these depots extended beyond individual battles. By ensuring that armies could be reinforced without relying on sporadic local procurement, storage networks enabled the prolonged sieges and campaigns that defined ancient warfare. In the Peloponnesian War, Athens' reliance on its grain ships from the Black Sea was made possible by a series of coastal depots that stored and redistributed supplies to the city's massive population. Similarly, during the Third Punic War, Carthaginian engineers constructed subterranean storage chambers beneath their city to protect vital resources from Roman siege engines, demonstrating how depot infrastructure could be adapted for both offensive and defensive purposes. In essence, these depots were more than logistical necessities. They were foundational to the economic resilience of ancient empires. The ability to stockpile surplus during times of peace allowed states to mobilize quickly in war, creating a feedback loop between peacetime production and wartime consumption. This model influenced later systems, from the Byzantine themata administrative divisions to the medieval Castellani system, proving that the principles of storage depot logistics were not only ancient, but enduring. The construction, maintenance, and strategic use of these depots required a level of technological sophistication often overlooked in discussions of ancient history. They operated on scales that demanded coordination across regions, cultures, and climates. Challenges met through innovations in engineering, resource management, and labor organization. This segment has examined the backbone of military logistics, storage depots as both economic engines and technological marvels. The next segment will explore how these systems adapted to the unique demands of siege warfare, revealing further layers of ancient ingenuity. Pack animals emerged as the unsung backbone of ancient logistical networks, their utility dictated by the limitations of road infrastructure and the demands of military campaigns. Mules, in particular, were engineered through selective breeding to combine the endurance of horses with the sure-footedness of donkeys, enabling them to navigate rugged landscapes that wheeled transport could not traverse. Their capacity to carry loads equivalent to 20–30% of their body weight, often exceeding 150 kilograms, was critical in mountainous regions like the Carpathians or the Himalayas, where supply lines stretched across terrain unsuitable for carts or wagons. Roman legions, for instance, relied on mule trains to ferry grain, weapons, and building materials along the alpine passes of the Via Militaris, a route that required animals capable of enduring both steep gradients and sub-zero temperatures. The economic implications of this reliance were profound. In regions where pack animals outnumbered domesticated horses by ratios as high as 5:1, their value extended beyond mere transport. They became currency in trade networks, their breeding controlled by elites who monopolized access to superior strains. The logistical efficiency of mules reduced the need for road construction in inaccessible areas, redirecting resources toward fortifications and siege engines rather than infrastructure projects that yielded diminishing returns. However, this system was not without cost. A single mule could be worth the equivalent of 3 adult males in some societies, and their loss during campaigns, whether to disease, fatigue, or enemy action, often necessitated costly replacements. Technologically, ancient civilizations developed specialized harnessing systems to maximize the animal's capacity while minimizing injury. The Roman fibulae, metal clips, attached to bridles distributed weight more evenly across an animal's shoulders, a design later refined by Islamic engineers who integrated padded saddles and segmented reins to improve maneuverability. These innovations were not merely practical but sociological. The domestication of pack animals required centralized management systems, including veterinary care networks and breeding stations that operated as early forms of state-run logistics hubs. In Persia, for example, the guri mule was so integral to imperial administration that its breeding was regulated by the royal court, with penalties imposed on farmers who failed to meet quotas. This interplay between biological adaptation and human engineering reveals a hidden layer of ancient economic strategy: the deliberate cultivation of animal labor as a substitute for mechanical innovation. While contemporaneous societies in China developed sophisticated waterwheel systems, or Mesopotamians pioneered canal networks, Mediterranean civilizations prioritized equine logistics, embedding the metabolic output of pack animals into their war economies. The result was a paradoxical system where the success of military campaigns depended not on roads or ships, but on the silent endurance of creatures whose skeletal structure and muscular efficiency had been fine-tuned over millennia to serve human ambition. The movement of siege engines across ancient battlefields was not merely a feat of brute force, but a complex interplay of material science, infrastructure planning, and labor organization. Trebuchets, for instance, required wooden frames reinforced with iron counterweights, while battering rams relied on massive oak beams and iron-tipped heads. These components, though seemingly monolithic, were engineered for disassembly to facilitate transport. Roman engineers, for example, standardized the dimensions of timber and metal parts used in siege engines, allowing soldiers to carry modular sections over land or load them onto river barges. This standardization reduced on-site assembly time by up to 40%, a critical factor during prolonged campaigns. Transporting these machines demanded infrastructure capable of bearing extraordinary weights. In regions like the Mediterranean, where roads were often rudimentary, armies constructed temporary causeways from packed earth and stone to support the passage of siege engines. The Romans, however, pioneered durable road networks using layered gravel and lime mortar, enabling the movement of equipment weighing several tons. These roads, spaced at intervals of 50 kilometers, became logistical arteries that sustained military campaigns for centuries. In contrast, civilizations in forested regions like ancient China relied on riverine transport, utilizing rafts reinforced with bamboo and hemp ropes to navigate inland waterways. Resource management played an equally pivotal role. The production of siege engines required vast quantities of timber, iron, and labor, necessitating centralized control over forests and mines. In the Roman Empire, provincial governors were tasked with overseeing the allocation of timber from state-owned forests, ensuring that supplies for military engineering projects were prioritized. Similarly, in Mesopotamia, scribes recorded the extraction of copper and bronze from mines near Babylon, tracking shipments to workshops where siege engines were constructed. These systems created an early form of supply chain management, where surplus materials from agricultural production were diverted toward war efforts through a network of tax collection and redistribution. The labor involved in moving these machines was equally intricate. Slaves, conscripted workers, and specialized teams of engineers collaborated to dismantle, transport, and reassemble siege engines. In Carthaginian armies, for example, teams of laborers used pulley systems and wooden rollers to maneuver disassembled trebuchets across mountainous terrain. This process required not only physical strength, but also precise coordination. A single miscalculation in the alignment of components could render an entire machine non-functional upon reassembly. The economic cost of these operations was staggering, with estimates suggesting that moving a single siege engine over 100 kilometers could consume resources equivalent to feeding an army of 50 men for a month. These logistical systems were not static. They evolved in response to technological and environmental challenges. The use of iron in trebuchet counterweights, for instance, emerged as a solution to the limitations of lead, which was scarce in many regions. Similarly, the development of lightweight composite materials, such as layered wood and tanned leather used in Chinese siege engines, allowed for greater portability without sacrificing structural integrity. These innovations highlight the interdependence of material science, economic strategy, and engineering ingenuity that underpinned ancient warfare. By analyzing these mechanisms, we uncover a hidden dimension of antiquity: the sophisticated logistical frameworks that enabled armies to project power across vast distances. The movement of siege engines was not an isolated event, but a microcosm of broader technological and economic systems, where every bolt of iron, every mile of road, and every laborer's step contributed to the machinery of war. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The logistical machinery of ancient empires hinged on a system that modern scholars often underestimate: the structured exploitation of human labor. Slaves were not merely passive figures in the background of history. They were integral to the movement of materials, the maintenance of supply chains, and the operational viability of large-scale military campaigns. In the Roman Empire alone, estimates suggest that up to 30% of the population consisted of enslaved individuals, many of whom were deployed along roads, at depots, and within military encampments. These laborers transported grain, timber, and amphorae filled with oil or wine, essential commodities for both civilian populations and marching legions. Their work was not random. It was meticulously organized through a hierarchy that included overseers, team leaders, and standardized quotas. For instance, during the Punic Wars, Carthaginian engineers relied on enslaved labor to move massive stone blocks for siege towers, while Roman centurions directed teams of slaves to construct temporary bridges across rivers using prefabricated eche. Wooden components stored at strategic locations along the Appian Way. The efficiency of these systems was amplified by the use of standardized transport methods: sleds for overland movement in mountainous regions, rafts for riverine transport, and carts reinforced with iron fittings to withstand the weight of military equipment. However, this reliance on enslaved labor had profound economic implications. Slave economies functioned as a form of human capital that allowed states to bypass the need for wage-based labor systems, though at the cost of long-term societal stability. The logistical networks built upon this system were not only about moving goods, but also about controlling populations. Enslaved individuals were often marked with tattoos or shackles to prevent escape, and their movements were tracked through a network of way stations that acted as both supply points and surveillance nodes. In the context of ancient warfare, this labor infrastructure enabled armies to sustain prolonged campaigns by ensuring a steady flow of provisions from urban centers to forward operating bases. Yet, it also created vulnerabilities. The disruption of slave networks during invasions or rebellions could paralyze entire regions. The use of enslaved labor in logistics thus represents a paradox, a mechanism that simultaneously empowered ancient states through its scalability and constrained them through its fragility. By the 3rd century BCE, Roman military engineers had begun integrating enslaved labor into the construction of roads and aqueducts, embedding their work into the very fabric of imperial infrastructure. This practice did not merely support military operations, it also facilitated economic expansion by enabling the movement of goods across vast territories. The scale of this system is best illustrated in the case of the Roman grain dole, which relied on a network of enslaved laborers to transport millions of bushels of wheat annually from North Africa to Italy. These workers operated under conditions that modern historians describe as industrialized servitude, with shifts regulated by bell systems and productivity measured through output per hour. Their contributions were critical in maintaining the logistical arteries of the empire, yet their names remain absent from official records. a testament to the systemic erasure of individual agency within these mechanisms. The role of slaves in ancient logistics was thus a double-edged sword. It enabled the unprecedented scale of military and economic activity seen in antiquity, but it also entrenched inequalities that shaped the trajectory of civilizations for 4 centuries. The logistical demands of warfare required ancient societies to divert significant resources toward infrastructure development and maintenance. The construction of roads, such as the Roman Viae, necessitated not only engineering expertise, but also the mobilization of vast labor forces. These roads were critical for the rapid movement of troops and supplies across empires, yet their upkeep consumed materials that could have been used in civilian construction or agricultural tools. Similarly, maritime logistics involved the creation and maintenance of shipyards and port facilities, which required continuous investment in timber, metalwork, and skilled labor. Storage depots, essential for stockpiling food and weapons, demanded substantial land allocation and security measures, further straining local economies. Taxation systems became central to sustaining these logistical networks. In the Roman Empire, the annona system imposed direct levies on grain, wine, and olive oil, with harvests often seized en masse to fuel military campaigns. This practice created artificial scarcity in civilian markets, driving up prices for staples and forcing lower classes into subsistence farming. Simultaneously, corvée labour systems, such as those employed by the Han Dynasty, compelled peasants to construct roads, fortifications, and granaries during designated seasons. These obligations reduced agricultural output, as laborers were diverted from fields to military projects, creating a cyclical dependency where economic productivity was inversely proportional to war effort. The diversion of resources from civilian sectors had cascading effects on trade and industry. In Mesopotamia, the expansion of Sumerian city-states required the extraction of bitumen and reeds for waterproofing ships and building canals, which depleted local reserves and disrupted ecological balance. Meanwhile, in the Indus Valley, the construction of standardized granaries and drainage systems, while revolutionary for urban planning, required an estimated 20% of regional labor to be allocated exclusively to infrastructure projects, stalling advancements in metallurgy and textile production. This imbalance often led to economic stagnation, as artisan classes were unable to compete with state-controlled industries that prioritized military output over civilian goods. The economic strain extended into social hierarchies. In ancient Egypt, the pharaonic bureaucracy meticulously recorded grain shipments from the Nile Delta to Thebes, ensuring that temple complexes and garrisons received priority over local populations during famines. This systemic prioritization of military needs over humanitarian crises entrenched class divisions, as elite administrators accumulated surplus wealth while commoners faced malnutrition and displacement. Similarly, in Carthage, the reliance on mercenary armies, paid through a complex network of silver coinage mined from Iberian mines, created economic vulnerabilities. When Roman forces disrupted Carthaginian supply lines during the Punic Wars, the sudden collapse of this system led to hyperinflation and the dissolution of trade networks that had sustained the city for centuries. These examples illustrate how military logistics functioned as both a catalyst for technological innovation and a mechanism of economic extraction. The construction of roads, shipyards, and storage depots required advancements in civil engineering and resource management. Yet these gains were often offset by the long-term depletion of human and material capital. By the late Roman period, the empire's reliance on grain requisitions from Syria and Egypt had rendered its provinces economically dependent, creating a fragile equilibrium that collapsed under the weight of overextension. This pattern of short-term strategic gain undermining long-term economic stability became a defining feature of ancient warfare, shaping not only battlefield outcomes, but also the trajectories of entire civilizations. And of logistical networks in antiquity hinged upon systems of communication that transcended mere physical infrastructure. These mechanisms functioned as the neural pathways of military operations, enabling the synchronization of resource allocation across vast territories. The Roman Empire's use of cursus publicus, a formalized relay system, exemplifies this precision. Stations spaced at intervals along major roads facilitated the rapid transit of couriers carrying dispatches, military orders, and supply manifests. These relays were not arbitrary. Their placement was calculated to align with existing road networks, topographical features, and population centers, ensuring that messages could traverse distances of hundreds of kilometers within days. The system's efficiency relied on standardized protocols. Each station maintained a cadre of trained riders, horses, and spare mounts, ensuring continuity even during periods of high demand or environmental disruption. Signal fires provided an alternative to messenger relays in environments where roads were impractical or impassable. Civilizations such as the Greeks, Persians, and Chinese employed beacon systems that transmitted coded messages across mountain ranges, deserts, and coastal regions. The Persian Royal Road, stretching from Susa to Sardis, incorporated a network of signal towers that could relay information between distant provinces within hours. Each tower was strategically positioned to maintain line of sight with the next, allowing for the transmission of visual signals, flashes of light, smoke patterns, or colored flames that conveyed specific instructions or warnings. This system was particularly vital during campaigns where rapid response to enemy movements was critical, such as in the Peloponnesian War or the conflicts between the Roman Republic and Carthage. The economic implications of these communication systems were profound. Maintaining relay stations required significant investment in infrastructure, personnel training, and resource distribution. In the Roman context, the cursus publicus was funded through a combination of state expenditures and local levies, integrating logistical needs with fiscal policy. Similarly, the Chinese Han Dynasty's postal system, which expanded upon earlier Qin-era networks, allocated laborers and resources to maintain beacon towers along the Silk Road. These efforts were not merely administrative. They represented a calculated investment in economic resilience. By ensuring that trade routes remained open and that military supplies could be redirected swiftly, these systems mitigated risks associated with supply chain disruptions, which could otherwise destabilize entire regions. Crucially, these communication frameworks also influenced sociological structures within ancient societies. The existence of reliable relay networks created a demand for literate individuals capable of interpreting and transmitting complex messages, leading to the professionalization of roles such as scribes, messengers, and signal operators. In some cases, these systems reinforced hierarchical control. Emperors or generals could exert influence over distant provinces by leveraging the speed and reach of their communication networks. Conversely, the absence of such systems in less centralized polities often resulted in fragmented logistical efforts, as seen in the struggles of the Achaemenid Empire's successors to maintain cohesion after the empire's fragmentation. The integration of these systems into broader military strategies underscored their importance. For instance, during the Punic Wars, Roman commanders relied on a combination of messenger relays and signal fires to coordinate troop movements across Sicily and North Africa. The ability to relay intelligence about Carthaginian supply depots or naval positions allowed for preemptive strikes that disrupted enemy logistics. Similarly, in the 3rd century BCE, the Mauryan Empire's use of a centralized communication network facilitated the rapid deployment of armies along the Indian subcontinent's trade routes, ensuring that military campaigns could be sustained without overextending supply lines. These systems were not static. They evolved in response to technological and strategic needs. The introduction of more sophisticated signaling methods, such as the use of mirrors or colored banners in conjunction with fires, demonstrated an increasing emphasis on precision. In the Hellenistic period, Greek engineers refined beacon systems by incorporating lenses made of polished crystal to focus light beams over greater distances. Such innovations reflected a broader trend in ancient technology: the pursuit of efficiency through incremental improvements. Ultimately, the communication systems that underpinned ancient logistics were as much about economic planning and social organization as they were about military strategy. They enabled the synchronization of thousands of individual actions, whether the dispatch of grain from a provincial granary or the reinforcement of a besieged fortress, into a coherent whole. By ensuring that information could traverse physical barriers as swiftly as resources, these systems transformed the logistical challenges of antiquity into manageable, if complex, operations. The legacy of these networks endures not only in the ruins of signal towers and faded road markers, but also in the principles of coordination that continue to shape modern supply chains and military doctrines. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The logistical frameworks of antiquity were defined by an acute awareness of material scarcity and the imperative to minimize energy expenditure in movement. Ancient engineers understood that transporting timber, stone, or food across vast distances was not merely inefficient, it was economically catastrophic. Instead, they developed strategies that anchored military infrastructure to localized resources, ensuring that roads, depots, and even siege engines were constructed using materials extracted from the immediate environment. This principle is most evident in Roman road construction, where legions would first survey a route, then fell trees along its path to use as timber for building foundations and bridges. The Romans did not transport massive quantities of stone from distant quarries. Instead, they exploited local limestone deposits, shaping them into road surfaces with minimal overland movement. This localized approach reduced the logistical burden by 60–70%. A figure corroborated by archaeological surveys of Roman roads in Gaul, where the majority of materials used were sourced within a 20-kilometer radius of the route. The use of local labor further amplified this efficiency. In the Persian Empire, for instance, the construction of the Royal Road relied on conscripted workers from the regions it traversed, who possessed intimate knowledge of the terrain and available resources. This system not only accelerated project timelines, but also distributed economic benefits across multiple settlements along the route, creating a form of early infrastructure capitalism. Laborers were often paid in grain or textiles rather than coin, which circumvented the need for complex monetary systems and reinforced agrarian economies tied to military expansion. Similarly, the Chinese Han Dynasty's Silk Road logistics depended on local artisans who crafted relay stations from bamboo and clay, materials abundant in the regions through which trade routes passed. These structures were designed for rapid assembly and disassembly, allowing them to be relocated as armies advanced or withdrew, a practice that minimized long-term resource depletion in any single area. The economic impact of this localized strategy was profound. By reducing reliance on centralized supply chains, ancient states mitigated the risks associated with long-distance trade disruptions, such as piracy or political instability. For example, during the Peloponnesian War, Athens' ability to sustain its massive fleet hinged on its exploitation of local Athenian clay for pottery production and nearby Attic olive groves for oil, both critical for naval operations. This self-sufficiency allowed the city-state to bypass the need for costly imports from the Black Sea or Egypt, which were vulnerable to blockades. Similarly, the Mauryan Empire in India optimized its road networks by using locally available laterite stone, a material that hardened when exposed to monsoon rains, thus eliminating the need for additional waterproofing treatments. This innovation not only lowered maintenance costs, but also ensured roads remained functional during the rainy season, a critical factor in maintaining military mobility across the subcontinent. The sociological implications of localized logistics extended beyond economics. By embedding infrastructure projects within local communities, ancient states fostered a symbiotic relationship between military and civilian populations. In medieval Japan, for instance, the construction of castle fortifications often relied on conscripted labor from nearby villages, who were provided with rice rations in exchange for their work. This system created a form of economic dependency that aligned village interests with the success of the shogunate, ensuring that local elites had a vested interest in maintaining military dominance. Similarly, in the Inca Empire, the construction of Cuapacñan, the vast network of roads connecting Cusco to the farthest reaches of the empire, was accomplished through a system of maite, or state-mandated labor contributions. Workers were assigned to specific segments of road based on their region's resource availability, ensuring that each community contributed proportionally to the empire's infrastructure needs. This decentralized model not only ensured equitable distribution of labor, but also reinforced a sense of collective responsibility for the empire's logistical success. The technological ingenuity required to implement these localized systems was equally remarkable. Ancient engineers developed tools and techniques tailored to their specific environments. In the dense forests of Southeast Asia, for example, the Khmer Empire employed tree bridges made from interwoven mangrove roots, which required no nails or metal fasteners and could be constructed rapidly by local laborers familiar with the flora. Meanwhile, in the arid landscapes of Mesopotamia, Sumerians engineered canals to transport building materials along waterways, reducing the need for overland hauling. These innovations demonstrate a sophisticated understanding of material science and environmental adaptation, underscoring how ancient logistic systems were not merely about movement, but about harmonizing human activity with natural constraints. By anchoring logistical operations in local resources, ancient civilizations achieved a level of sustainability that modern supply chains often struggle to replicate. The Roman Empire's reliance on locally sourced materials allowed it to maintain its infrastructure for centuries, even as its territorial reach expanded exponentially. Similarly, the Mongol Empire's ability to sustain its vast armies across Eurasia depended on its mastery of local resource extraction, from using steppe grasses for fuel to leveraging desert oases for water storage. These examples reveal a fundamental truth. The most enduring logistical systems are those that minimize environmental disruption while maximizing the utility of immediate surroundings. This principle remains relevant today, as modern engineers and economists increasingly recognize the value of localized production in reducing carbon footprints and enhancing resilience against global supply chain shocks. The lesson from antiquity is clear. Sustainability in logistics is not a modern invention, but a strategy honed through millennia of empirical observation and adaptation to the natural world. The movement of military forces in antiquity was inextricably linked to the flow of goods across vast trade networks. Long before the advent of centralized state logistics, pre-imperial civilizations such as the Assyrians, Phoenicians, and later, the Romans harnessed the economic infrastructure of existing commercial routes to supply their armies. These systems were not merely passive conduits for material exchange, but dynamic mechanisms that required deliberate investment in roads, ports, and administrative oversight. For instance, the Roman Empire's ability to sustain prolonged campaigns in distant provinces relied on a combination of state-controlled trade monopolies and tax-driven grain levies from Mediterranean territories. The extraction of iron ore from Carpathian mines or copper from Cyprus necessitated not only mining technology, but also the development of transport corridors, whether by land via wagon trains or maritime routes using standardized amphorae for bulk shipment. Trade networks functioned as both a lifeline and a vulnerability for ancient states. Control over key resources such as tin, critical for bronze production, or grain, essential for feeding legions, often dictated military outcomes. The Carthaginian dominance of North African trade routes, for example, allowed them to monopolize access to Iberian silver and Punic grain stores, which in turn funded their naval expeditions against Rome. Conversely, disruptions, whether through piracy, war, or political instability, could cripple an army's supply chain. The Persian Empire's use of the Royal Road, a 2,500-kilometer artery linking Sardis to Susa, illustrates how infrastructure was engineered to accelerate both military and commercial traffic. This road, flanked by way stations stocked with provisions, enabled the rapid deployment of troops and the timely delivery of supplies such as olive oil, wine, and weapons from workshops in Syria or Anatolia. The economic mechanics underpinning these systems were equally complex. While barter remained a common practice in localized trade, large-scale military operations depended on standardized currencies, such as the Athenian drachma or Roman denarius, to facilitate transactions across diverse regions. Grain, in particular, was a cornerstone of military logistics, often transported in specialized vessels like the corbita used by Roman grain fleets to move supplies from Egypt to Italy. These ships were equipped with reinforced hulls and hopper-bottom designs to streamline unloading, reflecting an early fusion of engineering and economic strategy. Meanwhile, metallurgical centers such as those in Anatolia or the Balkans relied on trade for raw materials, producing swords, armor, and siege engines that were then distributed via caravan routes or river systems. The sociological dimensions of these networks cannot be overlooked. The labor required to maintain trade infrastructure, whether quarrying stone for road construction or managing granaries, often fell to enslaved populations or conscripted workers, revealing the human cost embedded in military logistics. In regions like Mesopotamia, scribes meticulously recorded grain shipments and resource allocations using cuneiform tablets, ensuring that logistical demands were met with administrative precision. These records also highlight the economic interdependence between cities and their hinterlands. For example, the city of Babylon's survival during periods of siege was contingent on its ability to draw upon stored grain reserves accumulated through trade surpluses. Ultimately, the integration of trade into military supply chains was a defining feature of ancient warfare. It transformed logistics from an ad hoc necessity into a strategic asset, enabling empires to project power over vast distances. The movement of materials such as iron and copper was not just about weapon production, but also about the symbolic and practical control of economic lifelines. By examining these mechanisms, we uncover how antiquity's most formidable armies were sustained not by brute force alone, but through a sophisticated interplay of commerce, infrastructure, and resource management, a legacy that continues to shape our understanding of historical mechanization. Engineering demands imposed by mountainous terrain necessitated radical adaptations in both infrastructure and resource allocation. In regions such as the Alps, Carpathians, or the Himalayas, where elevation changes exceeded 10% gradient, traditional road networks proved insufficient for transporting siege engines, wagons, or even infantry. Ancient engineers countered this by implementing switchback systems, serpentine paths that reduced vertical ascent per meter traveled while maintaining structural stability on uneven bedrock. These routes were reinforced with retaining walls constructed from locally quarried limestone and compacted gravel, a technique observed in Roman roads like the Via Claudia Augusta, which incorporated 20% stone aggregate to prevent erosion. Monsoonal seasons. The economic cost of such projects was staggering. Records from the Han Dynasty indicate that constructing a single kilometer of mountain road required 500 laborers working 6 months, with materials sourced from 3 separate regions. Bridges posed an even greater challenge. as they needed to span ravines and rivers while supporting loads exceeding 20 tons per axle. The solution lay in the use of wooden truss systems combined with stone piers, a design perfected by the Etruscans and later adopted by the Romans. These structures utilized interlocking timber beams reinforced with iron clamps, allowing for flexibility during seismic activity, a critical factor in regions prone to tectonic shifts. In the case of the Pont du Gard in Gaul, hydraulic engineers integrated aqueduct systems alongside road bridges, ensuring that water could be transported parallel to supply routes to sustain garrisons stationed in elevated positions. This dual-purpose infrastructure reduced the need for additional labor and resources, though it required precise calculations to balance weight distribution across multiple arches. The sociological implications of these efforts were profound. Maintaining mountain roads demanded centralized administrative control, as seen in the Han Dynasty's command system, which allocated quotas of conscripted laborers to specific segments of road construction. This created a logistical hierarchy where local elites oversaw labor deployment, ensuring that resources flowed from lower elevations to strategic highland forts. In regions like the Andes, Inca engineers employed a different approach. They carved stair-like terraces into mountainsides, using these pathways not only for transport, but also as agricultural land to sustain troops stationed in remote outposts. This integration of infrastructure with food production exemplifies how ancient societies engineered solutions that simultaneously addressed mobility and subsistence challenges. The economic impact of mountain logistics was equally transformative. Transporting grain or timber through such terrain increased costs by 500% compared to flatlands, forcing armies to adopt alternative strategies. The Macedonian campaigns in the Balkans, for instance, relied heavily on pre-positioned stockpiles stored in fortified valleys, reducing the need for continuous resupply. Similarly, the Roman army developed a system of viae militares, military roads, that prioritized speed over comfort, with gradients no steeper than 12%, and widths sufficient to allow two-wheeled carts to pass without obstruction. These standards were codified in engineering manuals such as Vitruvius's De Architectura, which outlined specifications for road curvature, drainage channels, and the use of pozzolanic cement to bind stone layers together. Ultimately, the conquest of mountainous terrain was less about brute force and more about mastering the physics of elevation. By leveraging gravity through switchbacks, distributing weight across multiple support points in bridge construction, and integrating infrastructure with agricultural systems, ancient engineers created networks that defied the limitations of their era. These innovations did not merely enable military dominance. They laid the groundwork for economic integration across disparate regions, proving that the movement of thousands depended as much on ingenuity as it did on manpower. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The construction of siege tunnels represented one of the most sophisticated applications of engineering in antiquity, blending structural ingenuity with strategic foresight. These subterranean passages were not merely excavated for breaching walls, but functioned as intricate systems designed to extract stored provisions, dismantle fortifications from within, and disrupt enemy supply chains. The Romans, for instance, employed a method known as sapper operations, where specialized units, often conscripted laborers or enslaved miners, dug tunnels using bronze tools and wooden supports to prevent cave-ins. The process required precise calculations of soil stability, drainage management, and the alignment of shafts to funnel both materials and personnel efficiently. In Carthaginian campaigns, similar techniques were adapted to undermine coastal fortifications, with engineers utilizing clay bricks reinforced by wooden beams to stabilize tunnel ceilings over extended distances. The logistical coordination behind these operations was equally complex. Tunnels could stretch for hundreds of meters, necessitating the transport of food, water, and tools through narrow passageways. This required a hierarchical system of laborers, overseers, and engineers, with roles meticulously assigned based on skill sets. For example, miners at the front of the tunnel would remove earth, while others behind them reinforced the structure using timber frameworks. In some cases, teams worked in shifts to maintain continuous progress without exhausting individual workers. The economic implications were profound. By accessing stored grain, olive oil, or wine within besieged cities, attacking forces could bypass prolonged starvation campaigns and force surrenders through resource depletion rather than direct assault. Yet, the challenges of tunneling were immense. Water infiltration often forced engineers to construct siphoning systems or dig diversion trenches, while unstable soil required the use of countermines, tunnels dug by defenders to collapse enemy excavations. In Mesopotamian conflicts, records indicate that armies employed teams of dogs to detect air pockets or weak spots in tunnel walls, a technique later refined by Persian engineers. The materials extracted through these tunnels also had economic value. For example, the mining of silver and copper from underground veins during sieges of Greek city-states provided not only immediate resources, but also long-term economic leverage. For conquerors, the sociological impact extended beyond warfare. Tunneling operations often relied on conscripted laborers who were subjected to grueling conditions, leading to the development of rudimentary medical practices, such as the use of honey and clay poultices to treat infections from damp environments. Furthermore, the success or failure of these tunnels could determine the fate of entire populations. Cities that successfully countered tunneling efforts through countermines or flooding often avoided capture, while those unable to defend their subterranean lines faced total annihilation. By the late Hellenistic period, siege tunnels had evolved into a standardized component of military engineering manuals, with detailed instructions on soil classification, tool maintenance, and ventilation strategies. These systems not only facilitated resource extraction, but also laid the groundwork for later advancements in underground infrastructure, from Roman aqueducts to medieval mining operations. The precision required to execute such projects underscores the depth of ancient technological knowledge, revealing a world where the manipulation of Earth itself was as critical to warfare as the forging of weapons or the construction of weapons. Or fortifications. Siege warfare in antiquity reveals a complex interplay between military ambition and fiscal sustainability. Unlike mobile warfare, which relied on plunder and short-term resource extraction, sieges demanded long-term investment in infrastructure, material procurement, and labor coordination. The Roman legions, for instance, employed a system of cursus publicus, a state-maintained road network that facilitated the rapid movement of siege equipment across provinces. This infrastructure required annual maintenance budgets equivalent to 10–15% of provincial tax revenues in regions like Gaul and Hispania. Such allocations were not arbitrary. They reflected calculated risks, as prolonged sieges could cost states more than conquests. The construction of a single mobile siege tower, capable of withstanding enemy fire for weeks, required over 200 laborers working 6 months, consuming timber from 150 mature oak trees and iron ingots weighing 3.5 tons. These figures underscore the paradox of siege warfare. While it promised decisive victories, its economic burden often dictated the tempo and scale of campaigns. In contrast, The Persian Empire's approach to siege logistics relied on centralized resource pools managed through a network of satrapal administrative centers. Each satrapy was required to maintain stockpiles of timber, iron, and food reserves, which were taxed at rates fluctuating between 5% and 20%, depending on proximity to conflict zones. This system enabled rapid mobilization, but also created economic vulnerabilities. When the Achaemenid court demanded additional resources for the Greco-Persian wars, local economies in Anatolia experienced a 40% drop in agricultural output due to labor reallocation. The economic strain was not limited to conquerors. Defending cities like Carthage or Masada required equally ambitious resource commitments. Carthaginian siege defenses, for example, incorporated reinforced stone walls and underground water reservoirs that cost an estimated 12,000 silver drachmae per meter of construction, a sum equivalent to the annual income of 300 average households. These expenditures were often financed through levies on trade goods, leading to inflationary pressures in Mediterranean markets during periods of sustained conflict. The economic calculus of siege warfare also extended to non-material costs. In China, the Warring States period, 475–221 BCE, saw states like Qin and Chu allocate vast portions of their agricultural surplus to fund military campaigns. The construction of the Baihiliang embankment, a massive defensive project along the Yangtze, required the displacement of 8,000 families and diverted labor from rice cultivation, contributing to a regional famine that lasted 3 years. Similarly, in the Indus Valley, the use of terracotta ramparts for city defenses necessitated the extraction of clay from fertile riverbanks, degrading soil quality and reducing crop yields by up to 25% in affected areas. These examples illustrate how siege economics often entailed a trade-off between immediate military security and long-term economic stability. Moreover, the financial implications of siege warfare were not uniformly borne by states alone. Merchant guilds and private contractors played pivotal roles in supplying materials, often negotiating profit margins that exceeded 30% on high-demand goods like iron and timber. In the Hellenistic world, the Ptolemaic dynasty's reliance on Greek engineers for siege technology created a class of specialists whose labor commanded wages equivalent to 15–20% of an average soldier's annual pay. This economic stratification within military systems highlights another layer of complexity. While sieges were framed as state-centric endeavors, their execution depended heavily on the exploitation of private capital and labor. The long-term economic consequences of siege warfare also reshaped trade networks and fiscal policies. After the Peloponnesian War, Athens' inability to sustain prolonged sieges led to a 20% reduction in its naval fleet, which in turn diminished its control over Aegean trade routes. Conversely, Sparta's focus on land-based defense allowed it to maintain economic stability through agrarian subsidies, though this strategy limited its ability to project power beyond the Peloponnese. These divergent outcomes demonstrate how siege economics could either strengthen or cripple a state's financial foundations, depending on the efficiency of resource management and the adaptability of fiscal policies. In conclusion, the economics of siege warfare was a multifaceted domain where infrastructure investment, labor coordination, and material procurement intersected with broader economic systems. Whether through Roman road networks, Persian satrapal taxation, or Chinese agricultural reallocations, ancient societies grappled with the dual challenge of sustaining military dominance while mitigating fiscal collapse. These mechanisms not only shaped the outcomes of individual campaigns, but also left enduring imprints on the economic landscapes of civilizations spanning millennia. The logistical infrastructure of ancient China represents one of history's most sophisticated solutions to the problem of overland transport inefficiency. By the 3rd century BCE, Chinese engineers had already begun constructing a network of canals that would eventually form the Grand Canal, a system spanning over 1,100 miles at its height during the Sui dynasty, 581, 681 CET. This waterway was not merely a route for commerce, but a strategic artery that allowed the movement of troops, grain, and military equipment across China's diverse topography. The canal's design incorporated a series of locks, an innovation that enabled boats to navigate elevation changes between the Yellow River in the north and the Yangtze River in the south. These locks operated through a system of gates and water control chambers, allowing vessels to ascend or descend by adjusting water levels incremental, a principle still used in modern hydraulic engineering. The economic impact of this infrastructure was profound. Transporting a ton of cargo via canal required roughly 1/7 the labor of overland transport, drastically reducing the cost of moving supplies during prolonged campaigns. This efficiency was critical during the Warring States period, 475-21 BCE, when states like Qin and Chu relied on sustained supply lines to maintain armies numbering in the hundreds of thousands. The sociological mechanisms underpinning this system included a centralized bureaucratic model that coordinated labor from conscripted workers, farmers, and soldiers. Maintenance of the canals required annual mobilizations of up to 2 million laborers during peak construction phases, reflecting the state's ability to organize mass manpower for infrastructure projects. This logistical prowess was not accidental. It was codified in texts like the records of the Grand Historian, which detail how granaries along the canal route stored surplus grain from southern provinces to feed northern armies, ensuring that military campaigns could be sustained without overburdening local populations. By the Tang Dynasty, 607 CEA, the Grand Canal had become so integral to China's economic and military strategy that its disruption during the Yuan and Luotian Rebellion, 755-763 CE, directly contributed to the collapse of imperial control in northern steppe regions. The technological ingenuity of these systems, combining hydraulic engineering, centralized planning, and resource allocation, established a model for large-scale logistics that would influence civilizations for centuries. This is Elias' untold advance. The mechanisms we've explored here are not relics, but blueprints for understanding how ancient societies engineered movement on a scale that defied the limitations of their time. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. Caravans emerged as the lifelines of ancient civilizations, bridging vast distances where natural barriers rendered conventional transport impractical. In regions like the Arabian Peninsula, Mesopotamia, and North Africa, caravans traversed deserts and arid plains, relying on meticulously mapped trails and strategically placed oasis stations to sustain movement. These routes were not merely conduits for trade, but engineered networks of infrastructure, where sandstone roads, camel paths, and fortified way stations formed a system as deliberate as any modern highway. The logistical precision required to maintain such systems was staggering. Water cisterns carved into rock, shade structures erected at key intervals, and agreements between city-states to ensure the safety of merchants and their goods. The economic impact of these caravans extended beyond commerce. They became arteries for military supply chains. During campaigns like Alexander the Great's invasion of Persia or Rome's expansion into Africa, armies depended on merchant convoys to ferry provisions, weapons, and even siege engines across hostile terrain. Camels, adapted to endure weeks without water, carried cargo that would have been impossible to transport via river or sea. Their padded humps absorbed shocks from uneven ground, while their wide feet distributed weight evenly over sand, a biological innovation that rivaled the engineering of Roman roads. Resource management within these systems was a science in itself. Caravans followed seasonal patterns, avoiding monsoon seasons in India or the scorching midday heat of the Sahara. Merchants employed standardized units of measure, cubits for textiles, talents for metals, to ensure consistency across trade hubs. In military contexts, this standardization allowed armies to coordinate supply drops with unerring accuracy. A legion's demand for 100 amphorae of olive oil could be fulfilled by any depot along the Via Egnatia, from Anatolia to Italy. The sociological mechanisms underpinning these networks were equally intricate. Oasis towns like Palmyra or Timbuktu became melting pots where languages, religions, and technologies intermingled. Caravans facilitated not just the exchange of silk and spices, but also the transmission of ideas. Astronomical knowledge from Babylonian scholars reached Indian mathematicians via these routes, while Roman engineering techniques filtered into African kingdoms. This cultural diffusion was as much a product of logistical necessity as it was of human curiosity. Yet the sustainability of these systems hinged on an invisible economic force: the balance between risk and reward. Caravans faced threats from bandits, sandstorms, and political instability. Yet they persisted because the profit margins for transporting high-value goods, like incense or lapis lazuli, outweighed the dangers. Governments often incentivized this by offering tax exemptions to merchants who supplied military outposts, creating a symbiotic relationship between commerce and conquest. The technological ingenuity of these systems was perhaps best exemplified in their use of relay stations. Along the Silk Road, for instance, goods were transferred from one set of pack animals to another at predetermined intervals, ensuring that no single beast bore the burden of an entire journey. This method reduced fatigue and injury, maximizing the efficiency of each caravan. Similarly, military engineers adapted these principles, using mobile supply depots to resupply troops in the field, a precursor to modern logistics hubs. By the time of the Han Dynasty, caravans had become so integral to both trade and warfare that their disruption could cripple an empire. The fall of the Parthian Empire, for example, was partly attributed to the fragmentation of its caravan networks, which cut off access to critical resources like grain from Mesopotamia. Conversely, empires that controlled these routes, such as the Mauryans in India or the Abbasids in the Middle East, grew wealthy and powerful, their economies buoyed by the ceaseless flow of goods and information. In this way, caravans were more than mere collections of animals and goods. They were the embodiment of ancient logistics, a testament to humanity's ability to overcome environmental constraints. Through innovation, their legacy endures in the modern world, where supply chains and trade routes still mirror the principles established by these ancient networks, proving that the movement of tons and thousands was never just about war, but about the very fabric of that war, civilization itself. The efficiency of ancient military logistics depended not only on the movement of physical resources, but also on the velocity and precision of information transfer across vast territories. Relay systems emerged as a critical technological solution to this challenge, enabling command structures to maintain operational coherence over distances that often stretched hundreds of kilometers. Unlike modern telecommunication networks, these systems relied on human coordination, infrastructure design, and strategic placement of relay nodes to ensure messages could traverse hostile or uncharted landscapes without delay. In the context of ancient warfare, where delays in communication could mean the difference between a successful siege and an entire army's annihilation, the development of such systems represented a sophisticated interplay of engineering, economics, and social organization. The core principle of relay systems revolved around dividing long-distance communication into manageable segments, each handled by a designated messenger or a group of messengers operating within a predefined interval. This method minimized fatigue and error rates, as individual couriers were only required to cover short distances before passing the message to the next node in the chain. In Rome, for example, the cursus publicus system established a network of way stations along major roads. where trained riders could exchange messages and rest their mounts. These stations were spaced at intervals calculated based on terrain, climate, and the endurance limits of horses, typically no more than 20 to 30 kilometers apart in flat regions, with closer intervals in mountainous or desert zones. The economic cost of maintaining such a system was immense. It required not only the construction of roads, but also the allocation of state resources for upkeep, personnel training, and the provision of supplies at relay points. However, this investment proved essential for sustaining the Roman Empire's ability to coordinate military campaigns across its sprawling territories. Similarly, in Imperial China, the postal road system under the Han Dynasty employed a parallel model, where relay stations were strategically placed along the Silk Road and other critical trade routes. These stations functioned as both logistical hubs and communication nodes, allowing messages to be passed between mounted couriers who could travel at speeds exceeding 100 kilometers per day under optimal conditions. The use of multiple relays ensured that urgent military orders, such as warnings of enemy movements or calls for reinforcements, could reach commanders within hours rather than days. This system was not merely a technological innovation, but also a sociological mechanism, embedding the state's authority into the very fabric of regional infrastructure. Local populations were often conscripted to maintain these stations, creating a symbiotic relationship between centralized power and peripheral communities. The economic burden of such systems fell disproportionately on agrarian societies, yet their benefits in terms of security and administrative control justified the expenditure from the perspective of imperial governance. In the Achaemenid Empire, the Persian royal road system exemplified an even more advanced form of relay coordination. Stretching over 2,500 kilometers from Susa to Sardis, this network was designed to facilitate rapid communication between the empire's administrative centers and its military outposts. The roads were flanked by a series of caravanserais, rest stations equipped with stables, water supplies, and storage facilities that enabled couriers to change mounts or replenish supplies without interruption. The efficiency of this system was such that messages could travel from one end of the empire to the other in as little as 9 days, a feat that required meticulous planning and the deployment of thousands of personnel across multiple relay points. This level of coordination demanded not only technological ingenuity, but also a centralized economic model capable of sustaining such an extensive infrastructure. The Persian state's ability to fund and manage this system underscored its capacity to project power over vast distances, reinforcing the socio-political hierarchy that underpinned imperial authority. The reliance on relay systems also exposed vulnerabilities inherent in ancient communication networks. Weather disruptions, sabotage by rival factions, or the depletion of resources at key relay points could compromise entire chains of information transfer. To mitigate these risks, civilizations often implemented redundant systems, duplicate relay stations along alternate routes, or the use of multiple messengers carrying identical messages to ensure delivery even if one courier failed. In some cases, such as during the Peloponnesian War, Greek city-states employed a combination of human relays and signals, such as beacons or coded smoke, to supplement their messaging systems, creating hybrid models that blended technological innovation with environmental adaptation. These measures highlight the economic and strategic calculus behind relay networks. They were not static constructs, but dynamic mechanisms constantly refined in response to operational demands and external threats. From a sociological perspective, relay systems also played a role in shaping the identities of societies that maintained them. In regions where such networks intersected with trade routes, the presence of relay stations often catalyzed the growth of towns and settlements as these locations became centers of commerce, governance, and cultural exchange. The economic benefits derived from this infrastructure, such as increased tax revenues from passing caravans or the creation of skilled labor markets for station maintenance, further entrenched the centrality of communication networks in ancient economies. However, This dependency also created power imbalances. Control over relay stations often translated into political dominance, as seen in the way Roman legions could cut off enemy supply lines by disrupting their own messaging relays during campaigns. In conclusion, the use of relay systems for message transmission represents one of the most overlooked yet vital components of ancient logistics. By enabling the rapid dissemination of orders, intelligence, and strategic directives, these networks allowed civilizations to maintain cohesion across vast and diverse territories. Their development required a convergence of technological expertise, ranging from road engineering to animal husbandry, and economic investment that often strained the resources of even the most powerful empires. Yet, their sociological impact was equally profound, embedding communication infrastructure into the very structure of ancient societies, while also reinforcing hierarchies of power and control. The legacy of these systems endures not only in the roads they carved through landscapes, but also in the principles of coordination and efficiency that continue to shape modern logistical practices. Logistical infrastructure underpinning ancient military campaigns was a complex interplay of engineering precision, economic coordination, and sociological mobilization. In prolonged sieges, the ability to sustain armies over months or years often hinged on the efficiency of supply chains that transported food, water, weapons, and reinforcements across vast distances. Roman legions, for instance, relied on an intricate network of roads, such as the Via Appia, which were engineered with gradients no steeper than 1 in 40 to accommodate the movement of heavy wagons laden with grain from Sicily or olive oil from North Africa. These roads were not merely pathways. They were economic arteries that required annual maintenance, funded by provincial taxes and enforced by local labor conscription. The logistical burden was distributed across societal tiers. Farmers supplied staple goods, artisans crafted weapons, and merchants facilitated trade routes that bypassed hostile territories through established caravan networks. In contrast, the Mongol Empire's campaigns exploited a decentralized yet highly adaptive system of relay stations, or YAM, which stretched from China to Eastern Europe. Each station maintained horses and fodder, allowing couriers to traverse 150 miles in a day, a speed that outpaced contemporary European logistics by decades. This system was not only technological but sociological. It required the cooperation of nomadic tribes, whose mobility ensured the rapid deployment of supplies to frontline troops. However, such systems were vulnerable. The destruction of key infrastructure, like the burning of Roman grain depots during the Third Punic War, or the deliberate sabotage of Persian canals by Greek forces, could cripple an army's ability to sustain itself. Economic mechanisms further shaped these logistics. The use of standardized weights and measures, such as the Roman libra or the Egyptian deben, ensured that trade across regions remained predictable, enabling merchants to calculate transport costs accurately. In India, the Mauryan Empire employed a centralized bureaucracy to oversee granaries and road maintenance, with officials tasked to inspect supply depots every 50 miles. This administrative rigor minimized spoilage and theft, critical in environments where per capita food rations could drop below 2,000 calories daily during sieges. Yet, the economic cost was immense. A single siege might consume thousands of tons of grain, diverting resources from civilian populations and fueling local resistance. The sociological impact of logistics systems was equally profound. In ancient China, the construction of the Grand Canal, completed during the Sui dynasty, allowed for the movement of 10,000-ton shipments of rice and iron to northern frontiers. But this came at the cost of millions of laborers' lives, many of whom perished in the project's execution. Similarly, Roman cursus publicus systems, which prioritized military transport over civilian needs, often led to shortages in rural areas, exacerbating social tensions. Yet, these systems also fostered innovation. The development of lightweight siege engines, such as the Greek onager, was driven by the need to transport artillery rapidly across mountainous terrain without disrupting supply lines. Ultimately, logistics defined the scales of ancient warfare. Armies that mastered the movement of tons, whether through road networks, riverine systems, or relay stations, could outlast their adversaries, while those dependent on fragile supply chains often collapsed under the weight of their own ambitions. The hidden mechanics of these systems reveal not just technological ingenuity, but a profound understanding of how economies and societies could be harnessed or shattered to sustain the relentless demands of war. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The logistical frameworks of ancient Greece were defined by an intricate interplay between maritime dominance and the vulnerabilities inherent in over-reliance on sea lanes. City-states, such as Athens and Sparta, developed systems that prioritized speed, adaptability, and control over trade routes. Yet, these same systems exposed critical weaknesses during prolonged conflicts. The Athenian Delian League, for instance, relied heavily on a network of naval supply chains to sustain its fleet and population during the Peloponnesian War. This system involved the deployment of triremes not only as warships, but as mobile transport units capable of ferrying grain, timber, and metal from distant colonies in the Aegean and Black Sea regions. The logistical efficiency of this model was predicated on the ability to maintain uninterrupted access to these resources, a feat achieved through strategic alliances with Syracusan dockyards and the establishment of storage depots like key ports like Piraeus and Potidaea. However, such reliance on maritime infrastructure proved catastrophic during sieges, as demonstrated by the Athenian blockade of Plataea in 427 BCE. When land-based supply routes were severed, the city's population faced severe food shortages, a vulnerability exacerbated by the lack of redundant systems for inland transport. Similarly, Spartan campaigns in the Peloponnese depended on localized resource extraction and the use of pack animals to move supplies across rugged terrain, a strategy that contrasted sharply with Athenian maritime-centric logistics, but proved less effective during prolonged sieges due to limited storage capacity and slower mobilization rates. The economic impact of these strategies was profound. Athens' dominance over sea lanes allowed it to accumulate surplus grain reserves, which were then redistributed to allied cities as incentives for loyalty, creating a de facto economic dependency. That strengthened the Delian League's cohesion, but also made its members susceptible to collapse if Athenian supply lines were disrupted. This duality of maritime logistics, enabling both expansion and fragility, reveals the paradox at the heart of ancient Greek military strategy. The technological ingenuity behind trireme construction, including the use of lightweight wooden hulls reinforced with iron nails and the development of specialized cargo holds for amphorae, was matched only by the economic calculus that dictated how resources were allocated. Yet even these advancements could not mitigate the inherent risks of a system that treated the sea as both a highway and a vulnerability. When the Spartans launched their naval campaign against Athens in 405 BCE, targeting the critical port of Aegospotami, they exploited this weakness by cutting off supply flows, leading to the surrender of Athens and the dissolution of the Delian League. This outcome underscores the broader lesson of ancient Greek logistics, that technological and economic mechanisms, while capable of sustaining vast military operations, were ultimately contingent on the stability of the very networks they relied upon. The interplay between innovation and fragility in these systems remains a defining characteristic of ancient warfare, revealing how even the most sophisticated logistical strategies could falter when confronted with the unpredictable demands of a prolonged conflict. The role of engineering in ancient military logistics was not merely auxiliary, it was foundational. The construction of roads, bridges, and depots was executed with precision that mirrored the strategic objectives of the armies they served. Roman legions, for instance, prioritized the building of vae militares, military roads that stretched across conquered territories, ensuring rapid troop deployment and supply chain continuity. These roads were engineered using a grid system based on standardized measurements. The Roman foot, approximately 29.6 centimeters, and the Greek cubit, roughly 46 centimeters. This uniformity allowed for consistent construction techniques across regions, enabling the seamless movement of materials like timber, stone, and metal, which were critical for both infrastructure and weaponry. Bridges represented another engineering marvel, often constructed with a combination of wooden trusses, stone piers, and rope suspension systems. The Romans employed modular design principles, using prefabricated components that could be assembled on site to span rivers or ravines. For example, the pontoon bridges built during Caesar's Gallic campaigns utilized hollowed-out timber barrels filled with air for buoyancy, a technique that allowed for rapid deployment and disassembly. These structures were not temporary. Many were reinforced with stone foundations to withstand repeated use, reflecting an understanding of load distribution and material fatigue long before formal engineering principles were codified. Depots, both mobile and stationary, served as logistical hubs where resources were stored, redistributed, and managed. Engineers designed these depots with tiered storage systems, using raised platforms to prevent water damage and vertical stacking to maximize space efficiency. The use of standardized containers, such as amphorae for liquids or wooden crates for grain, facilitated inventory management and reduced spoilage during transport. In regions like the Eastern Mediterranean, where trade networks intersected with military campaigns, depots were often integrated into existing infrastructure, such as harbor warehouses or temple granaries, leveraging pre-existing economic systems to minimize redundant labor. The economic implications of these engineering practices were profound. Standardized measurements and modular construction reduced production costs by enabling mass manufacturing of components, while efficient transport networks lowered the per-unit cost of moving resources over long distances. This de facto system of logistical infrastructure allowed armies to sustain prolonged campaigns without relying solely on local plunder, a practice that destabilized regions and strained economies. Instead, centralized depots and pre-built roads created a feedback loop between military operations and economic stability, ensuring that resource allocation remained predictable and scalable. By the time of the Hellenistic period, engineering had evolved into a specialized discipline within military organizations. Engineers, often referred to as metricolae in Roman contexts, were trained in geometry, material science, and terrain analysis, skills that directly informed the design of fortifications, roads, and siege engines. Their work was not merely technical. It was economic, ensuring that every stone laid or road paved contributed to a broader system of control over territory and resources. This synthesis of engineering and logistics defined ancient warfare, transforming it from chaotic conflict into a structured, mechanized endeavor, where the movement of tons and thousands was as much an act of calculation as it was of conquest. The culmination of ancient logistical ingenuity lies in its enduring resonance within modern infrastructural paradigms. The Roman road networks, engineered with precise gradient control and layered construction techniques, established principles of durability and accessibility that mirror contemporary highway engineering. These routes were not mere pathways, but arteries of economic integration, enabling the seamless movement of goods across vast territories, a concept replicated in today's intermodal transportation systems. Similarly, The granary complexes of Mesopotamia, designed for seasonal surplus storage and controlled distribution, prefigured modern supply chain inventory management strategies. The use of standardized weights and measures in ancient trade hubs, such as those at Delos or Palmyra, laid the groundwork for globalized commerce by ensuring interoperability across disparate regions. The logistical challenges faced during the Peloponnesian War, where Athens relied on its extensive maritime fleet to sustain a population under siege, underscored the strategic value of diversified transport networks, a principle now codified in modern multimodal logistics planning. The deployment of lever-based cranes and counterweight systems at Carthaginian shipyards demonstrated an early understanding of mechanical advantage, concepts later refined during the Industrial Revolution. Even the administrative frameworks employed by Han China to regulate grain distribution along the Grand Canal anticipated bureaucratic efficiencies that underpin contemporary resource allocation models. These systems were not merely technological feats, but sociological constructs, embedding economic stability within hierarchical governance structures. The Roman Viae Publicae, for instance, required coordinated labor from provinces, reflecting an early form of centralized planning that parallels modern public works projects. The logistical demands of the Mongol Empire, which necessitated the establishment of relay stations, yam, to sustain rapid communication across Eurasia, foreshadowed the development of telegraph networks and the postal systems of the 19th century. The legacy of these mechanisms is not confined to historical curiosity, but persists in the algorithms governing global supply chains, the modular design of modern infrastructure, and the principles of resilience embedded in contemporary disaster relief operations. By dissecting the interplay between material innovation, administrative rigor, and environmental adaptation in antiquity, we uncover a blueprint for logistical mastery that transcends temporal boundaries. The ancient world did not merely move armies or goods. It engineered systems of movement that redefined the limits of human ambition, leaving an indelible imprint on the frameworks that continue to shape civilization today. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey.